tail end of the first part, but I think it's, if I don't make it all the way through my second part, then that's okay. It's just my research is kind of what's at the end, so that's the least interesting part probably. So I guess where we were was talking about trying to address issues with the gap, with the materials gap and the pressure gap, and just showed an example where the perceived pressure gap is in fact a materials gap. And I think it's coming to light now that that's true in a lot of cases, although I won't show all the examples, that really the materials gap is often a bigger issue than the pressure gap. All right, and so one possible materials gap, if you want to call it that, all right, is the fact that, as I mentioned before, reactions tend, especially dissociation reactions like the dissociation of nitrogen, tend to want to happen on steps of surfaces rather than on flat surfaces, because atoms at the step are more coordinatively unsaturated, and so they're more willing to form bonds. So they're more willing to break the nitrogen-nitrogen bond. Right, and that's what's seen for the dissociation of a number of different molecules. So we have diatomic nitrogen, NO, O2, and carbon monoxide on a variety of different surfaces. And what the Norskov group has done is plot up the dissociation energy, the barrier to dissociation for a variety of these molecules versus the adsorption energy, or versus, I guess this is the D band center of the molecules. All right, so this is versus an electronic structure parameter that we may talk about a little bit about later. But the main point that I want to get across is that there's a linear relationship with the dissociation barrier and this electronic structural parameter for a variety of different metals. And that's true on the flat sites, and it's also true on the step sites. And actually these lines are parallel to each other, and they're just displaced by about -1 eV on the step sites. And so it turns out that a lot of the studies that people had done typically on flat, perfect surface planes are pretty readily extendable by just a difference in energy to the step sites. Right? And so you can generally observe the same kind of trends just at a faster rate on step sites. And this has been done, of course, when we use single crystals, we aren't restricted to flat surfaces. We can choose surfaces that are truncated at step sites. So for example, a 211 FCC site that has a controlled density and type of steps. And that's really how a lot of this work was done. I guess most of these numbers are computational numbers, but they've confirmed these with selected experiments as well. Okay, one concept that I wanted to get to at the beginning of this time to make sure that we don't shortchange it, because it is a critical concept for a lot of what we'll talk about, is known in catalysis as Sabatier's principle. And kind of defines what we'll call the sweet spot in catalysis. Right, and the idea typically is that you can track a key intermediate on the surface, so say atomic nitrogen in the ammonia synthesis process. And the most active kind of catalyst, if we look at a variety of different metals, so let's say we look at iron, ruthenium, nickel, platinum, silver, and we plot up the log of the reaction rate for the ammonia synthesis process on the y-axis, and just the adsorption energy, so the delta H of adsorption, the thermodynamic property for atomic nitrogen, say, that there would be some point in the middle that would be associated with the highest activity. And if the adsorption energy were too negative, so that's very strong adsorption, then we'd have intermediates that are bound too strongly. And if the adsorption energy is too positive, then the intermediates are bound to be bound too weakly. And so the idea here, so maybe if I can think of a quick analogy. So let's say that, so my goal as a faculty member is to produce as many PhD graduates from my group as I can. I don't know if that's accurate, but let's say that it was. And if I wasn't an attractive enough advisor in the sense of being attractive to work for, then I wouldn't have many students wanting to stick to my group. And so my group would not have a very high population inside the group. And so because of that, I wouldn't be able to produce many graduates, even if I was a very good advisor while they were there. And if they got into the group, they got out quickly, but they just never seemed to come in. And so that would be the case of weakly bound intermediates, that your throughput is limited by the ability to bind to the surface. Right? In the case of intermediates that are too strongly bound, I'm a very popular advisor, right? But I make life too good for the students while they're in my group and they never want to leave, because Boulder is a nice place where I work. And so they end up staying for 8-year PhD projects. And even though I can get lots of people in my group, I can't really get them out. They're taking up all the slots so that I can't get a lot of throughput. Right? And so I'm sorry for that, it was, as you can tell, an impromptu analogy, so not a very good one. Right? But the idea is that if we apply that to surfaces, right, that if we have weakly bound intermediates, we have a clean surface, so there's lots of sites ready to go to do the reaction. But they're not attractive to the adsorbates that are going to come in and react. Right? So the reaction doesn't happen. If we have intermediates that are really strongly bound, all of the surface is tied up, so there are no more sites that can do the reaction, and the stuff that's there isn't leaving because it likes to be there. Right? And so what you want is something kind of in between. You want it to be attractive to intermediates, but not too attractive. And a lot of the strategies that we'll look at for searching, for example, for better fuel cell catalysts, or water oxidation catalysts for photoelectrochemical cells, are focused on trying to find this optimal point. Right? And they're relating this adsorption energy for a key intermediate along the pathway to the rate, and then in turn relating this to the electronic structure of the material. Any questions about that? Let's see. So actually, I forgot I had this example in here. So this is a fairly recently published example of using this kind of strategy. This is for a refinery kind of application. So prior to ethylene polymerization, you have some acetylene in the feed that actually screws up the ethylene polymerization reaction for making polyethylene. And you want to get rid of that acetylene, but it's acetylene, small amounts of acetylene that are floating in a sea of the desirable feed, which is ethylene. And so you want to selectively do this, but not keep on adding hydrogen to make that. Okay, and so again, in order to find an optimal catalyst, what these researchers did was track a key intermediate, and actually this isn't an intermediate in the reaction, but it tracks with the absorption energy of intermediates in the reaction. And they can find sort of a sweet spot that's defined by this white box here that corresponds to sort of the ideal absorption energy for this hydrocarbon type intermediate, the simple methyl intermediate. Right? And so they find that there are a number of materials in this box. And so what they did was they plotted basically the price per metal loading, price per kilogram of the metal for all of these different catalysts. Right? And they found one that was much, much less expensive than the one that's commercially used, which I have to walk over here to see it. So palladium silver is the commercial catalyst, and you can see that it's many orders of magnitude more expensive than this nickel zinc. But they found, I don't show the plot here, they found in their studies that nickel zinc catalyzed the reaction just as well as palladium silver, costing something like 0.1% as much. Okay, so this strategy, this group in particular that published this work uses this quite often to find new catalyst compositions on the basis of Sabatier's principle, that there's some sweet spot in the absorption energy of an intermediate that is going to correlate with rate. And in this case, you can find ones that have roughly equivalent rate for which the metal cost is a lot lower. Okay, so I think I'll just go ahead and skip that summary. Any questions at this point? We start talking about biomass refining.
So are these sweet spots, I mean, is this something that you can find very easily, either experimentally or theoretically? Like how tight are they, and how do you actually?
Yeah, so it depends on what the intermediate is as far as what the desired absorption energy is. So there's not a universal absorption energy for intermediate X that you're looking for. So it's different for different species. But these volcano plots show up pretty universally in these sorts of simple reactions. Where things get a lot more complicated and they don't work so well yet is in reactions where you can have a lot of side products. And selectivity is also an issue. So the reactions that it works pretty well for are reactions that you tend to not have a lot of branching of the intermediates on the surface, and everything's going down sort of a linear pathway. You can describe it with these fairly simple metrics. I think ultimately we'll be able to, for reactions with a lot of different pathways as well. Any other questions? Okay, so we're going to talk for the rest of this session on production of particularly fuels, but I might have a couple of chemicals examples from biomass, so trying to produce the same kinds of petrochemicals, but not from petroleum, using biomass as the feedstock. And this is a depiction of the molecular structure of one component of biomass, which is cellulose. Okay, and so just to remind you of where we are, we talked about a few applications of this, certainly not in encyclopedic coverage. Right, and now what we're going to talk about is less the process of photosynthesis itself, and more on deconstructing the biomass to try to make things like gasoline. Okay, and so what I want to focus on quite a bit is what are some of the unique challenges and also some opportunities associated with refining biomass compared to refining petroleum. And so you might think that potentially you have a carbon source here. Coal and crude oil are carbon sources. Why can't you just kind of feed them into the same sorts of processes? Right? In some cases, you actually can feed them into related processes. In some cases, you can't. So we'll talk about that. We'll talk about the types of catalysts and processes that are currently being used, and we'll actually try to connect some of those processes to what we'll see tomorrow when we talk about water splitting and fuel cell catalysis. That some of the processes are actually very similar. And then talk about sort of the unifying theme of all of this, which is how we can use surface studies to improve catalyst design. We have more limited time for that. Okay, this is just, probably should use more worldwide numbers. This is actually just U.S. numbers from the U.S. Department of Energy for how biofuels are expected to grow over the coming decade or so. And right now, we pretty much have gotten close to saturating the market with what are called conventional biofuels. So this is biodiesel from soybean oil, for example, or ethanol produced from corn. But those are not sustainable sources of biofuels. And then now we're switching over to more cellulosic biofuels. And I don't show this here, but as we go beyond 2022, this other category is going to need to grow. All right, and so cellulosic biofuels means not using the part that people eat, so not using the starch that's already a nice sugar that's relatively easy to work with and make fuels from, or an oil that also is relatively easy to make fuels from, but instead using like the stalks of the corn plant, for example, or using grasses that are composed of cellulose that people don't eat. And the reason people don't eat it is that it's very difficult to digest, and it's very difficult for our catalysts and reactors to digest it too, which is why it's such a big area of research in my field right now, trying to develop catalysts that can process cellulosic biofuels. Right, other advanced biofuels right now, it looks like is mainly going to come from algae, which you can harvest the algae itself and potentially convert it to biofuels, for example, or you can use the algae to produce a variety of chemical products, especially oils that can be useful for further refining. We'll talk about some of these different, especially cellulosic sources and what we can do with them. Okay, so what does biomass look like? Probably the biggest point that I want to make in looking at the composition, since this is obviously very complicated, is that in all of the different substances that are a part of biomass, there are lots of oxygen atoms. So you see all kinds of hydroxyl and ether and ester and carboxylic acid type functions inside biomass. One of the things that makes biomass difficult to deconstruct is there's lots of hydrogen bonding that occurs between those oxygen atoms. It sort of ties all the strands of the cellulose together, so it ties all the different polymer units, where you can kind of see a monomer unit here where there's hydrogen bonding in between the different units, and that can be very difficult to disrupt. The biomass typically, it depends on where you get it, so there are various sources. As I mentioned, you could be using corn stover, so the part of corn that you don't eat. You could be using something like switchgrass that's grown as a fuel crop on marginal lands, hopefully. You could be using woody biomass, scrap wood, for example, or wood from the beetle kills that we've had in our part of the U.S. And so, but in general, biomass is composed of roughly, say, 40% cellulose, which is this compound, and roughly, say, a quarter hemicellulose, which is related to cellulose, but is based on 5 carbon building blocks, whereas there are 6 carbon building blocks here. So glucose, for example, compared to xylose, are basically what these monomer units are. And so these compounds are related, and they tend to go through related processing. And we'll talk about some of that processing. And then the other component that's more difficult to deal with, because it has a lot of phenyl functionality, so a lot of substituted benzene rings as part of it, is lignin. And that typically has to be dealt with thermally, whereas you can deal with some of this enzymatically before you use heterogeneous catalysts. We'll talk about different approaches for dealing with those different parts of biomass. Okay, and so these are the main pathway. There are lots of sort of proposed solutions for converting biomass into fuels and hydrogen and chemicals. We're going to talk mainly about 3 different approaches. The first one we'll talk about is gasification, and this calls for just blasting the biomass with lots of heat, and so that you break it down to its most basic parts, which are carbon monoxide, as much of that as possible. You'll also get some carbon dioxide typically, and some other stuff that you don't want that contains carbon, as well as hydrogen. Right? And then you can use syngas to fuels routes that we'll talk about in just a minute to potentially make chemicals and fuels. All right, the next route that's typically used, especially with lignin, is pyrolysis, in order to make a substance called bio-oil that looks a lot like crude oil, but sure doesn't behave much like crude oil. We'll talk about that, and that needs catalysis for upgrading in order to make this. I should mention that all of these routes also need solid catalysts. And then we can take especially cellulose and hemicellulose and do hydrolysis to break it down into its component sugars. And then we can do a variety of steps. Some of them involve enzymes. I'll mainly talk about the use of solid materials to refine the sugars that you get into a variety of oxygenates and then ultimately into fuels and chemicals. And there, as I mentioned, there are other routes that people are looking at, but by far the most research is occurring in one of these 3 areas. Okay, so as I mentioned, one of the big issues and the reason you can't just feed a lot of these compounds straight into refining operations from a petroleum refiner is that hydrocarbons that you tend to derive when you crack crude oil tend to not have a lot of heteroatoms in them, not have a lot of oxygen atoms in them. And so their molecules, I just show a few examples, there are obviously hundreds of different compounds that you get in a refinery. This would be a more sort of too short for a diesel, but sort of a diesel type molecule. You would tend to find, not benzene hopefully, but phenyl rings in gasoline that they're trying to eliminate benzene, fortunately. And then you also get a lot of unsaturated hydrocarbons that are blended into the fuel mix. All right, with biomass, when you start breaking it down, you tend to get compounds that have quite a bit of oxygen functionality. And this is actually relative, what I show here is mostly relatively mild oxygen functionality, actually. You've already removed it, or already removed some of it. And the important thing to bear in mind about the oxygenate functionality is that anytime you have a functional group, there's going to be a pretty good tendency for it to want to bind to the types of catalysts that are used in refineries. So it's called a functional group for a reason. It's a handle on which you can do chemistry. And so selectivity is a huge issue in biomass refining, because you have so many points at which you can do chemistry and points at which you can attach too strongly to a catalyst and deactivate it on these kinds of molecules that are highly oxygenated compared to these kinds of molecules. They tend to be more homogeneous in their atomic composition. Any questions so far? Okay, so let's start talking about some of the processes. We'll start with the one that is at least that may be the simplest, and maybe one of the probably. So there are some plants that are trying to come online. They're having a little bit of difficulty actually with some of their processes that use this technology. And so this is treating the biomass, just heating it up to try to break it down into simpler parts. Right, and the first of those, as I mentioned, is gasification. That typically occurs at 800 degrees C and as high as maybe 1200 degrees C, maybe even slightly higher. And so you have to add a lot of energy into the process, which is one of the unattractive aspects if you're trying to recover energy from this. The general reaction that you want to do is kind of described here. So you use some combination of steam, and then typically you'll feed in some O2 in order to do some combustion that provides some of the energy that you need. But whenever you do that, of course, you're wasting some of the hydrocarbon feedstock. You're burning it to make CO2 and water instead of making fuel. Right? So that's a disadvantage. And then there's some stuff that it just seems like you can't break down, even going up to as high as 1200 degrees C thermally, and it gums up the works downstream in the process. Right? There's another potential problem with gasification. Pyrolysis, you try to partially break it down. I guess maybe another thing I don't like about gasification is you already have some nice 6 and 5 carbon units that are strung together in pretty intriguing ways. You just have also high oxygen content. And it would be nice not to break it all the way down and waste all the work that nature has done before you try to reassemble it to make hydrocarbon products. Okay, so there's some inherent efficiency disadvantages with doing it this way. In pyrolysis, you try to avoid some of those, so you try to partially break down biomass. This, as I mentioned, this is particularly used with lignin. And so it's a lower temperature process, so it requires less heat input, although it's still considerable. And it produces this bio-oil that I'll show a picture of in a minute that has pretty widely varying compositions and properties that unfortunately vary over time, actually, because it's not a stable formulation. And you can't just send this into a refinery, into an existing kind of refinery. The complex upgrading is required. So I don't want to say too much about the gasification process itself, because it's just using a lot of heat to break biomass down. One thing I did want to mention is that one interest that ties this a little bit into solar, although not solar photovoltaic, is it's just solar heat, is that there are a couple of startup companies that are trying to do this solar thermally. One of them was spun out of CU, where basically they have a reactor that they use a solar concentrator to heat the reactor up to 1200 degrees C so that they don't have to feed any oxygen. They use just energy directly from concentrated sunlight in order to get very high reactor temperatures. And so this is a startup that they're trying to bring online at a small production scale this year, I think. Okay, so this is a slide that I want to spend a little bit of time on. I know it's complicated and we won't look at all of this slide. But the question is, why do you want to make CO and hydrogen? How is that useful? And this is something that's going to come up when we look at water splitting and especially artificial photosynthesis type applications for photovoltaic materials tomorrow. Right, and so what you can do, synthesis gas ends up being a very useful product that you can make a lot of different compounds with. So you can react it over a metal catalyst. It would typically probably be an iron-based catalyst for the syngas composition that you get from biomass in order to make what's called Fischer-Tropsch liquids. And so this would actually primarily be diesel fuel, although you can also make olefins and gasoline. This is basically polymerizing carbon monoxide, making water as the byproduct. So you pull off the oxygen and polymerize the carbon and add hydrogen to it. Okay, so Fischer-Tropsch processing is one thing you can do from syngas. You can also use a metal catalyst, copper and zinc oxide, to make methanol, which is another potentially useful product that people have proposed using direct methanol fuel cells, for example. And also as a useful intermediate that you can react that over zeolite catalysts to make gasoline, for example. And it's called the MTG process, methanol to gasoline. And there are processes to get to ethanol, which there's sort of a mandate to produce a lot of as a biofuel. And a wrap that I wanted to particularly point out is that there's some interest in just trying to utilize the hydrogen. right? So using the hydrogen and hydrogen fuel cells, as we'll talk about tomorrow, and you can do a reaction called water-gas shift, WGS here, and that's reacting CO with water to make hydrogen and CO2. And we'll formally write that up tomorrow. So you make excess hydrogen and convert the CO to CO2. And some of the routes that we'll talk about tomorrow actually involve the reverse water-gas shift. So you want to take CO2 and hydrogen that we're going to get from water, hopefully, from doing water splitting, and go this direction so we can try to get the synthesis gas after water splitting and after CO2 sequestration, and then try to do some of the processing like Fischer-Tropsch to make liquid fuels that fit into the existing infrastructure. And so we'll see these kinds of processes coming up again tomorrow when we're doing solar-derived fuels. Okay, so pyrolysis, I don't think I'll bother with the flow diagram over here. Just wanted to show what pyrolysis oil looks like. You can see that it looks kind of like crude oil, pretty murky, very dark brown oil. But it doesn't have the properties of oil. It's still very highly oxygenated, very reactive. Actually, it has a very low pH. It's very acidic. It can be pretty corrosive to handling systems. And so it's not something that you tend to want to use directly, except maybe as a heating type fuel, not as a transportation type fuel. And so you need to be able to upgrade it. These are some of the types of compounds that you get when you subject lignin, which is the main component that people are looking at for pyrolysis, to pyrolysis. So Baluchistan is a sugar that you get. You get some of these other different oxygenated compounds. And you want to be able to upgrade those to things a little more like gasoline. And the main things that you try to do are reject oxygen either as water or reject it as CO2 and water by designing a catalyst to pull out the oxygen. And so this cracking process is sort of similar to the cracking that you do with oil, but they're working on trying to really improve the zeolite catalyst, because right now this reaction, although this is what you'd like it to produce, actually about 40% of the material goes to form coke on the surface of the catalyst, so it's totally wasted. And they have to burn off that coke during operation. And then hydrodeoxygenation is sort of a similar issue that you tend to poison the catalysts, which tend to be precious metals, so it's right now a very expensive process. Okay, what I wanted to spend most of the rest of the time on is the refining of sugars, which is maybe a little bit more studied area. It's a little bit cleaner area because you can get to fairly clean feedstocks, whereas when you treat things thermally, you tend to create sort of a mess of a soup of compounds. So if we take cellulose and depolymerize it, then we can get a variety of different sugars. So these are the ones that you get from cellulose, and then you get 5 carbon sugars that have an oxygen inside the ring with no carbon-containing side chain. If you break apart cellobios, or I'm sorry, if you break apart hemicycles, excuse me. I'll skip that. And so one of the reasons why I became interested in researching this area is that there are a lot of things that you can do with these sugars. Right? So it's both maybe a problem that you have all these functional handles on sugars, but it's also, if you can control selectivity, it's also an opportunity that you can make a lot of stuff from sugars that's hard to make from petroleum, because you have all these functional handles that you can use to attach sugars to other compounds to ultimately try to make a designer fuel type molecule. And so, again, I don't want to focus on the details of these different pathways, but you can take a lot of these pathways and get to molecules that are potentially interesting as fuels that, for example, have high octane numbers. Okay, and I don't want to get into, this is already looking like a little bit too much chemistry probably. Maybe I'll skip this one. It shows, well, maybe I'll skip the left-hand side here and focus on the right. Okay, and basically, so let's take, I just wanted to give you a feel for some of the ways that people are trying to make fuels from sugars. Okay, so you can take a sugar and treat it with hydrogen, and the ring structure of the sugar will pop open and make a polyol. All right, so it's, in this case, if you deal with a C6 sugar like glucose, then you'll form sorbitol, which is shown here. All right, and then you can do two things. You can either treat it under reforming conditions, which means treat it with steam and just try to break it down to make CO and hydrogen. So in a way, it's pretty similar to the gasification technology that I talked about. Just not as messy. You don't have to go to as high a temperature with this kind of compound. Or you can try to pluck off the hydroxyl functions one by one and get all the way to hexane, right, in order to make a hydrocarbon type fuel for applications. And so these involve combinations of oxide and metal catalysts that I don't think we'll talk about this example, but we'll talk about surface studies that people are doing in just a minute. This is just another example that another thing that you can do with the sugars that you pull off of cellulose is that you can dehydrate the sugars. And if you dehydrate glucose, then you make hydroxymethylfurfural, which is this compound, which also has some nice functional handles. And so the Demesa group at the University of Wisconsin has basically shown how you can make a variety of different carbon chain lengths doing different catalytic chemistry in order to make things that range from the jet fuel range to the gasoline type range, doing a variety of catalytic transformations that we don't want to go into all the details out here. But hopefully this gives you some idea for the types of chemistry that people are using, where here they're using the handles that they have to do chemistry, for example, to couple between different units before deoxygenating and making, for example, a C12 that can be used as a good jet fuel. Okay, so I'll spend just a few minutes talking about some of the kind of research that we're doing and a number of other groups are doing to try to bring a fundamental basis to catalyst design. The state of the field right now is largely that people have taken the same sorts of catalysts that are used in petroleum refining and just trying to change the composition and seeing if they work. And then there's some rational basis for them, but not a whole lot. They're just really trying to find things that work. And the work in the surface science area is trying to understand why those work and really how the high oxygen content affects the behavior of these kinds of intermediates on surfaces. So one example I talked about, so one of the key pathways I showed involves HMF as a key intermediate and showed how you could, for example, dimerize based on an alcohol condensation with that functional handle, right? But there are a lot of these 5-membered furanic type rings that end up being formed during biomass refining, during different types of chemical steps. And so one thing that our group and other groups are doing is just trying to vary the chemical structure in order to understand how different structural motifs affect the reactivity. And so, for example, one type of structure that comes up a lot is called a lactone. Right? So it's a cyclic ester that has this type of functionality group, this type of functional group, and has 4 carbons and an oxygen that make up a ring. And we can, by choosing our compounds, we can understand, well, some of those show up with a carbon-carbon double bond, some of them don't. How does that affect the reactivity? Just comparing the reactivity of those 2 compounds. How does another type of functional group that shows up commonly is a furan, so a cyclic ether that has this kind of functionality without the carbonyl hanging off. And so we can compare these two to understand how an unsaturated ester compares to an unsaturated ether. And we can do things like compare how the position of the double bond, or whether it's there at all, affect the reactivity. So those are a lot of the kinds of studies that are going on, are taking, because biomass involves very complicated molecules, taking basic structural motifs and understanding how they affect reactivity. Yeah, I think I've talked a lot about this. A lot of the work that we've done has involved these kinds of molecules. So comparing, maybe the one I didn't talk about was actually the ring size. So you can look at a very highly strained ring versus one that is relatively thermodynamically stable, in addition to the other kinds of compounds that are comparisons I talked about. And I'll, for the next maybe one slide, I'll talk about that particular comparison. And so actually, maybe in the interest of time, I'll just jump to the punchline. The way that we do these studies, again, is that we'll simply absorb the molecule at low temperature, and then as we heat the surface, we'll look for how the molecule is being transformed on the surface using, for example, vibrational spectroscopy, see what kind of reactions are taking place, characterize the structures with a combination of quantum chemistry, calculations, and experimental spectroscopic measurements. And then what this slide shows is that we can also see what kinds of reaction products are coming off. I'll skip all of that. And so there are several things that we can observe. I just want to try to give you a flavor for this kind of research, is that the presence or absence of a carbon-carbon double bond in these kind of ring structures and its position really play a critical role in how these species absorb and react on the surface. So if there is no carbon-carbon double bond, then the reaction always takes place through the oxygenate functional group. That's how the molecule comes down and binds, and that's the point at which it breaks open. Right? If there is a carbon-carbon double bond, it's pretty much always the case that that's what comes down and sits on the catalytically reactive surface first. So that's where the initial reaction takes place, although we can, as we heat the surface up, also get some ring opening reactions of the oxygen containing functional group. And then furthermore, the proximity of the carbon-carbon double bond, I know it doesn't show up very well here, but here's the carbon-carbon double bond in the case of 2,5-DHF, and it's here in the case of 2,3-DHF. The proximity strongly affects how strongly absorbed the molecule is, and that actually, although I didn't go through the story, it affects what reaction products you see when you study the reaction of 2,3-DHF versus 2,5-DHF. Okay, and so by understanding these factors, we're able to link up the more complicated reactions of different kinds of sugar and carbohydrate derivatives in order to build up a picture of how different structural motifs affect reactivity. There's some more. This one too, I think. We can also, for example, we'll touch on this one quickly, look at the effect of ring strain on the tendency of these molecules to react. And so what we see is at relatively low temperature, starting at around 180 Kelvin, but complete by 230 Kelvin, we see this big change in the surface vibrational spectrum when we start with this intermediate on platinum. And we can attribute that through some molecular models to this type of ring opening process. Whereas we have to go up to more like 300 Kelvin when we have a less strained ring. That corresponds to a significantly higher activation energy, and we produce different kinds of products as a result of that. I'll skip this too because of some of the other stuff. And I think I've talked about some of this stuff already too. I'll make sure I get to some of the stuff at the end. Okay, so I want to talk about some new directions in our group and that other groups are taking to look at trying to refine sugars and other biomass derivatives. And one of them is to realize, okay, you're dealing with a biologically constructed system when you're deconstructing biomass. And so maybe we can take some hints from the enzymes that were used in order to do that construction, in order to trying to control the selectivity for deconstruction. And so, for example, a lot of the reactions in biomass refining involve molecules that have more hydrophobic type regions in them. So take, for example, an unsaturated fatty acid. So you have an acid end that's very hydrophilic, and then you have a long hydrocarbon tail on that acid that's hydrophobic. Right? And those, if you want to react a certain region of that molecule, you'd like to create a local environment that favors absorption and reaction of a particular type of functional group. And so I'll show a couple of examples of this where we're trying to take an oxygenated molecule, so there's an example here, and modify the surface with sort of very crude enzyme mimics in a way, right, that are organic molecules that we can, in this case we're using a self-assembled monolayer of organic molecules that are tethered by a thiol functional group in order to modify the reactivity of toward oxygenated molecules. All right, and for this very simple probe reaction, what we're interested in is simply hydrogenating this carbon-carbon double bond. As you can see here, we're fully saturating it, but leaving this epoxide function alone, which is actually a very difficult thing to do, and something that they're still struggling with industrially, because the oxide is so ring-strung, it really likes to pop open, reacts at very low temperature. Okay, so what we can see is that when we use these self-assembled monolayer coatings, if we tailor them in the right way, right, then we can achieve, this is the selectivity on a typical, toward the desired product, it's about 11%. On a typical industrial catalyst, this is palladium supported on aluminum, but you could use a variety of different metals, and you get about the same result. This is a very difficult reaction to do selectively. When we modify the surface with these alkane thiols, we're able to achieve very high selectivities. That this shows a selectivity of about 90%. If we change the operating conditions, we can get to 99% with these kind of organic modified surfaces. And one interesting thing that we see is that the selectivity is pretty high across the board for a variety of self-assembled monolayers on our catalysts. So these are all alkyl ligands. These show alkyls terminated by a hydroxyl function for our self-assembled monolayer. We've looked at polyol self-assembled monolayers with phenyl groups, and a lot of them show these very high selectivities. But what's interesting is that what you see with the rate of reaction, which is these gray bars. And so you take a hit in the reactivity, but maybe not as much as we'd expect when we add the self-assembled monolayer to the palladium catalyst. And the reason for that is that we're occupying catalyst sites with our self-assembled monolayers. So that's not a big surprise, but we actually didn't, we were expecting an orders of magnitude drop off in the reactivity, and instead we only get a very modest drop off in the reactivity with the self-assembled monolayer. But maybe more interesting is that you actually get a much higher reactivity, for example, with a long hydrocarbon chain than with a short one. Right, so if you use a C3 tail, you think there would be, that's a very thin film, and you think it'd be very easy for the reactants to get in and react on the surface. Whereas with a C18 tail, that's a very lengthy chain, and you think it'd be hard to get in. All right, and so what we see actually is that we can take a vibrational spectrum of the self-assembled monolayer coated catalyst and pay particular attention to this particular stretching motion, which corresponds to the CH stretch of a methylene group. And we see that it is redshifted as we increase the chain length. And what that corresponds to is that we're getting increasing order of our self-assembled monolayer. Right, so the chains are becoming more closely packed, which is causing this kind of redshift. And so what we think is actually happening here, although this is pretty recent work, right, is that as we form these ordered arrays of bound organic molecules, we're forming channels, well-organized channels, that allow the molecule to move in between chains and do the reaction. Whereas when things are more disorganized, we don't have those nice uniform channels that allow access of the molecule to the surface, where we have a highly selective reaction because of the interactions with the self-assembled monolayer. Okay, and then finally, should be wrapping up pretty much on time here, similar approaches are being used by other groups, and wanted to point out one recent article from Science where they're dealing with actually lignin derivatives and trying to do selective reaction to those derivatives. And in this work, they're using sort of similar ideas, that they're taking conventional supported palladium catalysts. And what's interesting about a lot of the biorefining reactions is that you start with something that's very soluble in water, because it has a lot of oxygen content and is very polar. And as you start trying to remove some of the oxygen content, the molecule becomes more and more hydrophobic. Right? And so you have a lot of issues with transport between different phases. And so what this group has done is try to create basically a Janus particle that contains both a hydrophobic function and a hydrophilic function, and try to tailor the catalyst on those two functions, so that you get the reactions that you want in the aqueous phase, and then the reactant, as it becomes less soluble in the aqueous phase, can migrate over here and react on the catalyst that's on the other side of the interface in this oil phase, in order to continue to complete the transformation. And so this again is another indication of work that's going on to try to use organic ligands in order to control hydrophobic, hydrophilic interactions in biorefining applications. Okay, so to conclude, So there are some parallels of refining a biomass to petroleum refining, but what's really different and causes you to not be able to use a lot of the same catalysts and processes is that there's very high oxygen content. And because of that high oxygen content, selectivity is really a key issue. That you have a lot of potential sites for reaction, and so trying to design catalysts that are selective for that is important. And the recent big direction in the field is really trying to tailor hydrophobic-hydrophilic interactions at the surface in order to design catalysts to be more selective for the reactions you want to do. And so with that, I'll take any questions, and just as a preview of next time, we'll start talking about electrocatalysis for both water splitting and the reverse reaction, which is oxygen reduction, which is the key reaction in fuel cells. And then in the last session, we'll talk specifically about photoelectrocatalysis for water splitting. Any questions? Yeah.
Yeah, how does the energy compare, like if you compare cellulose-based biomass to, let's say, starch-based biomass, the energy that we need to actually make fuel?
So the energy that resides in the molecule is essentially